And we are live. Good afternoon, good morning, good evening, everybody. Welcome, welcome, welcome. We have another amazing workshop for you today. We're talking about smart contract tokens. Specifically, we're talking about MIST token, and we're here with the SLP guys. You probably have met them if you've tuned into our previous workshops. These guys are amazing. They're a partner with us here at Blockhack, and so we're super happy to have them with us again. We have James and JT here from the SLP team. How are you folks doing today?
Doing great. Thanks for having us on.
Awesome. Before we jump into the workshop and talk, I like to get to know our speakers a little bit better. I know you guys have been on the cast a couple times, so I'm been racking my brain to find some new questions to ask you guys. And I know you guys are problem solvers. You have several different projects going on, and so I want to ask you guys how you solve problems. Do you have any particular tips or tricks, things that you use in order to work your way through problems? I personally have my little rubber ducky, and sometimes when I have an issue, I'll talk the issue to my rubber ducky, and in doing that, I kind of stumble upon the answer or work it out. Do you guys have anything similar?
Yeah, good. First of all, I said this last week, but never give up. So perseverance, obviously, but it seems like whenever I go and take a walk or a drive, it just kind of pops in your brain, the solution to your problem. It's happened so many times.
Mm-hmm. Yeah, that's actually quite similar to my answer to that too. I get the most done when I'm not really doing much of anything for work at all. So anything from sleeping to taking a bath or whatever it is, it's you need breaks to really make progress. So
totally. There's that saying, like the shower aha moments, right? And I think like scientifically, it's like when you're under stress and when you're really trying to solve something, your brain tenses up, right? And like it constricts the neural pathways, and it's only when you like relax or find some peace that your brain can like process things. I find there's so many intricacies about our like brain neurology that we haven't fully like mapped out and understood yet. And to your point, JT, like the sleep thing, I woke up in the middle of the night last night and I was like, I just had this idea, and I've been keeping a notepad beside my bed, so I just like stumbled and like half eyes closed, like scribbled something on the paper. And it's kind of like, I don't know if you ever watched Jerry Seinfeld, the Seinfeld show. He that happens to him, and he writes something on a piece of paper, and then in the morning he can't read it. So he, like, the whole episode is him like going to his friends like, "Can you read this? What is this? What is this joke?" So that could also be your downfall to a certain degree. Awesome. Cool. So I think we're going to jump into the talk, but right before we do that, I also want to draw folks' attention to the bottom of the screen. We have an Ask a Question button down there. So if during the talk you have any questions for these guys, please drop it into the Ask a Question button. And if you see one there that you really want to get answered, give it an upvote, and we'll get to it as soon as we can. And just beside that, we also have a polls button. So go ahead and check out our polls. We want to know a little bit about your knowledge about smart contract languages. I see some votes coming in now. I wanted to know if you've ever used P2SH, which we're going to talk about today. I see some of you are like, P2S what? And and some of you are also like, oh yeah, I use P2SH all the time. And some folks we wanted to know also have used cache script before. Some folks don't know what cache script is yet, so we might touch on that today. And we want to know generally what your understanding or experience with smart contracts are previous today. So we'll take a look at those polls towards the end. But I think that is it for me for now. I'm going to pass it over to these lovely gentlemen who will take over the cast, And so I'd like you both to help, you all to help me welcome JT. He's the lead dev at SLP. He's the co-founder of Fountainhead.cash, which is a suite of developer services. And he's also an inventor of many of the SLP tools, which we talked about some of the tools in a previous talk. So you can go ahead and check out that talk that happened last week. We also have James Cramer. He's the lead developer and co-founder at Simple Ledger Inc. He maintains the SLP edition of the Electron Cash wallet. And previously, James worked as a civil engineer before hard forking his life into Bitcoin development. So I'd like everyone to help me give a digital round of applause to these lovely gentlemen as they take over the cast.
All right.
All yours, yeah.
All right. So, yeah, thanks for having us on. Today's workshop is called Bitcoin Cash Script and Smart Contracts for Achieving Token Wizardry with SLP. So there's a number of reasons or use cases why you might want to do smart contracts with SLP tokens. You can decentralize your token supply. You can specify a minting schedule for your token, similar to how Bitcoin has its minting schedule. You can have revocable token rewards where you airdrop people tokens and you can take them back if somebody doesn't use them. You can do staking. You could do decentralized exchanges, user authentication systems, scoring systems, central bank digital currencies, and possibly some DeFi applications such as yield farming. So I wanted to start off with a high-level advice for if you want to use SLP tokens and you want to use smart contracts. Our advice is that you have a goal in mind, something that you want to achieve, because that goal will allow you to persevere through all of the learning and playing around with code and stuff that it will take to successfully build a project. We're showing this simple graphic in a linear way where you read about Bitcoin, SLP, cash script, and then you're on to wizardry, but it's not always that way. Sometimes you might start with SLP. That might be why you're here. You might start with cash script and you learn about the others as you go. But in general, when you're building up your foundation of knowledge, you want to have a solid foundation in Bitcoin, layer on top of that with SLP, then go to smart contracts, and then on to your wizardry. Now, at each step of the way, you want to make sure you're doing reading. I recommend Mastering Bitcoin. I have a hard copy here. I was just referring to it today as I prepared for these slides because we're all noobs. And that was something somebody said that to me when I first got into Bitcoin, was that we're all noobs here. Even those of us who, like me, I'm here presenting today, but I still do consider myself a noob. The other thing that I think is important is that you have a peer. You've probably heard of peer programming. Have a peer that is on a similar level to you so that you can share and discuss your progress along the way. Obviously, you can always reach out to mentors and stuff, but having somebody who you can talk to on a daily basis is really useful. So I just wanted to cover some primitives here. This is a slide about the Bitcoin transaction format. And it's super simple. Basically, these larger blue boxes, each one represents a transaction. Within the transaction, on the left side, you have coming in inputs. You have the inputs of the transaction. On the right side of each box, you have the outputs of the transaction. Now, within each one of those inputs or outputs, there's special parameters. The inputs refer back to the previous transaction ID and the index of the output of the previous transaction. The input also has an unlocking script to prove This is also called a script sig, to prove that you have the authority to spend the Bitcoin in this transaction. The outputs have an amount and a locking script. And there's an index associated with each output. And these indexes or these outputs get consumed by the subsequent transaction. So it's very simple. You have locking scripts on the outputs, you have unlocking scripts on the inputs, and it just goes on and on. So you may not know this, but the full nodes, they don't necessarily maintain the full history of what's happened in the past. They always just maintain a list of unspent outputs. So when you hear that term, unspent outputs, it's just referring to an output that has not been spent yet to another transaction. So on the right side here, you see the two outputs. These are unspent. The full node would just keep these two in its records, and it would not have the rest of this information in its database. A lot of full nodes do keep that information so that people can use applications and refer to that data, but it's not necessarily necessary for mining. So script structure: every output has a locking script, every input has an unlocking script. Locking scripts in the outputs are referred to as script pub key in the transaction lingo, and then the unlocking scripts are referred to as script sigs. Now it's more than just a signature, and the locking script is more than just a pub key. So these are actual, this is actual code. It's in the script language, and there's more than just what those names provide. It's kind of confusing. There's two address types in Bitcoin. One is pay to pub key hash, and the other is pay to script hash. Your typical transaction is, and I should say this is Bitcoin Cash. I think Bitcoin Core has pay to witness, but we have pay to pub key hash. That's your typical transaction type or address type in Bitcoin Cash, and then you have pay to script hash, which you will be using for smart contracts. There's also legacy multi-sig and pay to pub key, but those don't have address types, and they're not really used anymore. So once you kind of understand the transaction format that I showed on the previous slide, you'll eventually be able to look at this blob. This is just a binary or hexadecimal encoded blob for a transaction, and you'll be able to just parse this thing out into its components. So I thought I would just do that here while we're talking. It's super easy. The first 4 bytes of the transaction are always the version of the transaction. The next byte is typically just 1 byte. It's a var int. It just says how many inputs are in this transaction. So we see 2 there. And then I usually go to the end of the transaction at this point, and I take off the last 4 bytes, which is the lock time. And then I start looking for common things in the transaction that I can identify. One common thing is this series of FE and then a bunch of Fs. That is the sequence, end sequence of a input. So we know that that's the last thing. We can separate that there. There's another series of Fs, so we can separate this. And then we see we knew there was 2 inputs, so we see those 2 there, and then we can see this next series, there's a 1, so that indicates outputs. There's 1 output, and we know that there's 8 bytes in the amount that's being sent, so we have the 1 output with the amount, and then this would be the locking script here. So, and then within this, the inputs, there's a script sig. So the first part of the input is a script sig, and this can be a little bit more complicated to parse depending on what kind of input it is. But that's generally how you can parse out a transaction, and you can do a lot of troubleshooting that way when you are using smart contracts. So I just want to talk a little bit more about the two different address types. There's custom scripts. Pay to script hash is required for custom scripts. It's also called locking script, or also called. It also has what's called a redeem script within it. So that's kind of confusing. I recommend that you take a look at the Mastering Bitcoin book in the explanation of pay to script hash there. I took a couple screenshots of from that book of the two different address types and how they kind of walk through step by step. I think I looked at this for hours before I understood it really well. But for pay to pub key hash, you have the locking script. I'm sorry, the locking script exists in the outputs. So that's shown here on the right. And then the unlocking script is in the inputs.
Sorry to interrupt, James. Are you able to go full screen with that?
Oh, yeah, sure.
It's a little smaller.
Sorry about that. Yep. Okay, so yeah, you could probably see that better now.
Yes, definitely. Thanks.
Yep, sure. So the red box shows the unlocking script. This is usually in a pay to pub key hash. This is what you have in the input. You have a signature followed by the pub key of the person who owns the private key, who's signing. And then you have the locking script, which was encoded in the previous output. And it's a very simple script. It just says duplicate. And it's a stack-based language. So what happens is it executes from left to right when the interpreter is looking at this. So it puts the sig on the stack, then the pub keys on the top of the stack, and then when you hit an opcode, it executes on the top item of the stack. So you're going to do an op dupe, which means you're going to duplicate the pub key. We know that was the top thing on the stack. And then you take the hash 160 of that top item, and then the hash will already be encoded there. So you're just going to check that the one that you calculated and the one that's encoded in the locking script are the same, and then you're going to check the signature that the signature validates with the pub key that was provided. Now, the next diagram from Mastering Bitcoin shows how to do a complex script with pay to script hash. This is just This is just a multi-sig script. Multi-sig is the simplest and most often used pay to script hash address. So I recommend when you're doing your reading and studying up on the subject that you just first understand how multi-sig works in the context of pay to script hash, and then go from there. So Bitcoin Cash has some really unique innovations, and it just makes it, in my opinion, way more powerful than other blockchains. And the key innovation, I think, is the opt-check data sig operation. It allows a transaction locking script. When it's executing, it allows you to introspect the details of the current transaction. So basically the script can know about the details of the transaction. And this allows you to pass in a summary of the transaction. And a lot of it's hashed summary, but it's basically you're passing in the signature hash pre-image, and check data sig can prove that the signature hash pre-image that you passed in about this transaction matches up with the signature that is also used to be verified against the transaction. So it allows you to put special constraints on the transaction, like specific input requirements or specific output requirements. Sending, one coin has to be sent to a specific address. So this is where the notion of, or the term covenant was brought in. is when once we had check data sig, people started building these covenants, lots of innovative ideas and stuff. But basically it uses the input signature pre-hash image or pre-image, and it puts requirements on inputs and outputs. So for example, you must have an output to a certain address with a certain value. You can do all the those types of things with a covenant. So there's one covenant that is really pretty cool. It's called Mist Coin. JT is going to talk a little bit more about the details of how Mist Coin works. It's a smart contract covenant, but it allows it's a decentralized token supply with proof of work mining. All of this works using script, smart contracts, and it has its own built-in schedule. This diagram here shows the Mist reward schedule. It started out at 400 or so tokens per block, and then currently we're down to like 80 tokens per block. So I'm just going to pass it off to JT now, and he's going to go into more details about Mist Coin. Let's see here. JT, are you sharing your screen?
Yeah, I am. Sorry, I was on mute. Thanks so much for the great introduction. Can you see my screen?
Looking
I
good.
can.
All right. Yeah, so Mist is one of the most interesting smart contracts, I think, in just in Bitcoin in general. It does a lot of things that I think a lot of people didn't really think was possible. And it's really only through the advancement of tools like Meep, the debugger that James showed, and these sort of scripting languages that make building something like this probably possible. So you can check out more information on mistcoin.org. This has everything you want to see. It has a whole sort of write-up on how it works. You can download some of the software for it. If I remember right, I think one of these has the script files and everything that you want to look at. But how this actually works is you basically have this covenant that restricts the minting baton UTXO to being stuck in this sort of loop where it can only do certain things, right? Like the minting baton can't really be burnt. It can't be transferred out of this. And it's limited to creating new tokens for people who provide the proof of work able for people to create a transaction that fits its requirements. So what we're going to do with this is actually go through line by line and show how the Mist token really works. So the Mist token is built using Spedin. This is a smart contract language, one of the most popular along with CashScript. And they're both actually quite similar. So right at the start of the Spedin contract, you'll see, in any Spedin contract, you'll see what looks like contract and then some name. And this will list the different variables that you initialize a contract with. So this has a handful, and we're going to reference back to some of these. But just so you can see quickly, the names should be pretty self-explanatory too. Another part with Spedin is you provide challenges. So a challenge is a way that you can spend this contract. And so this UTXO has potentially different challenges. For Mist, it just has one, and this is the generate function, and it could also be called mine or something similar. So generate is referring to the fact that this allows a person to generate new tokens by providing certain values here. So the user is actually sending in this data when they're trying to spend. And by spend, I mean use this in a transaction, because the spending is actually minting new tokens and sending those back to themselves. So this is going to look super hairy, but don't get too worried about it. So this is the PREIMAGE deserialization. And how a lot of these contracts work is you'll be passing in a PREIMAGE, which is basically this sig hash digest. And this link right here, oops, has all of the information about what this actually is referring to. And so this is all of the information about a transaction that you can recreate and then check in script. And so say the hash prevouts, previous outputs. So you can reconcatenate previous outputs, create this hash, and then provide the other information for this, do a double SHA-256, and you'll end up with this this value. So it's all protected with hashing, and so you can get you can validate transaction formats in a certain way. This you should spend a bit of time on and really read through. It's kind of dense, but looking at this, we don't have to go into like the specifics for each of this, but the @ symbol is splitting at a certain point. So this is 40 bytes away from the end of the PREIMAGE. And we're going down and we're getting these different values out of this. And this is a common pattern in Spedden when using covenants. Well, it's actually required. So you have to extract this data so that you can validate it later. So now we're into the meat of the function. And right to start off, we're going to actually check the signature, and we're going to check the data signature. And we're doing this with the SHA-256 of the PREIMAGE. So we're looking to see basically that this is a valid transaction, that what you passed in as a PREIMAGE is actually the transaction that you're signing for. And yeah, that's basically all that is to it. This ensures that you can't do fake transactions. It basically secures the data so that you can be insured of the later SHA-256s that you're doing on everything else. So this is sort of the safety check. And that's actually a pattern you'll see. So we're looking at height verification. What you'll notice with a lot of the array written contracts is that what you'll see over and over again is verify, or cache script does require, but you're basically building up these values and verifying that what they passed in actually matches those values. So it's kind of different than most programming, but for maybe like really defensive programming, it's kind of similar. But if you just think of it like, hey, someone could pass in literally anything, and we need to verify as we go, this is the correct data as we calculated. And sometimes you can skip some of these, but especially unless you have a really good reason to, it's probably better to be a little bit safe and don't over optimize too much, because you're saving some hundredth of a penny in transaction costs or whatever. So it's but so for this we're using one function. This matches to a Bitcoin opcode, and this just converts some bytes into an actual number. So the state T1 is the current block height, and we're just verifying that the contract state T0, so this was initialized at the start of the contract, is going to be equal to the token height -1. And you'll see, like, by initialize at the start of it, this is actually just the last transaction in kind of an interesting way, but we'll see that later. So similarly for the mint amount, we're going to perform a calculation to see that the amount that the user is attempting to mint actually matches with what the contract has calculated as the correct amount. So again, num to bin. So this halving interval, I forget what it is offhand, but I think it's like every 20,000 blocks or something. This increases. So yeah, you're doing like token height divided by, say, like 3. And then this is very SLP specific, but if you're doing any SLP smart contracts, you're going to run into this, and it might not be super obvious right away unless you picked up on it in the specs. But the endianness for SLP numbers is big endian. So Bitcoin deals with a little endian, and you're going to have to use this reverse bytes function to flip the bytes around for correct endianness. And now we're going to verify that the difficulty for this block has been reached. So what does that actually mean? Well, the user is passing in a minor solution, but this period means concatenation. So we're concatenating the preimage with a minor solution, and we're hashing that value. When we look at that value that we just calculated, and then we're grabbing, so this is the split operator again. Difficulty leading 0 bytes means how many bytes are we looking at for difficulty. So for this, we're going to get work as the first value here, the first however many bytes in this difficulty leading 0 bytes. And then we're going to convert those bytes into a number and check to see if that number is equal to 0. So basically what you're going to have is 1 byte equal to 0 that is empty. Well, hopefully 2 bytes, 0, 0, 0, 0 in hex, and so on. So you're really just checking the bytes for this. How many at the start are 0? They're not set to anything. And yeah, so every time there's a difficulty increase, it's pretty large, right? It's not a small number. It's 1 additional byte. So it really jumps up a lot. And this is one of the really cool things that misperforms. So it's actually going to create some state to pass along with this this covenant contract. And what the state is right here, that's actually the height, the token height. So we're increasing this each time that we run it, and we're creating a new contract that has this new state. So if you remember back to the start where we're initializing the contract, in most contracts you wouldn't reinitialize the contract from another contract. But with this one, you're increasing the height so that you can track this. So you could actually apply this to a bunch of other ideas and pass along data from UTXO to UTXO that has some transformation over time dependent on that transaction. This is a really simple example of that, but I think there's a lot of really interesting use cases where you could probably do more. And then what we're also doing here is we're laying out what the outputs actually look like, right? Like what are the outputs for this transaction going to be? And this is actually going to check against what the transaction that you provided is, right? Like, does it have the same outputs as what we just listed right here? So we have the metadata for SLP. This is all compressed, but maybe if you've looked at SLP specs enough, you might be able to pull out some of this stuff. The token ID and mint amount probably helps. Then we have the token pay to pub key hash. This is a pretty standard output. And the mint amount is actually going to end up being associated with the second output here. And then we have the baton, which gets sent back to the same sort of vault or covenant contract that's mutated. So we're sending it back to that. And when you do pay to script hash, it's the hash 160 of some script. So this is, we're building up the script here, and then we're going to make a pay to script hash that goes to that. And so this is how it's really stuck. Like, there's not a way to release this UTXO from this sort of loop that's in, where it's just able to mine new coins. So that means, some small amount of BCH is sort of considered burned in a way because it's trapped in this, but it's a very small amount, so I don't think it's much of a worry. And we're going to use those three outputs and actually verify that this is correct. And so this goes back to where we're parsing the preimage before. Hash 256 does a double SHA-256, and in this case, it's concatenating those three outputs, those three output byte strings, and it's comparing it to a single hash of the hash output. The hash output we got from that slide where we're breaking apart the preimage. And you can see in the right here in the digest algorithm. So this allows us to do the check data seg and verify that this is the same transaction. Someone's not just passing in a random one. And we're actually able to validate that the outputs from this mining transaction fit some pattern that we specified during the last slide. This is a little bit more simple. We're just checking the lock time. So token height is it started at 0 for the first missed block, and it's just adding that to the starting block height, which the script was created with or initialized with. So if we're able to complete all of these items, we have a successful mining transaction. We would have passed in a preimage for a transaction that sent sent output of the baton back to this script. We would have provided a value that would have hashed along with the preimage to something that had required difficulty, and we would have sent those tokens to a transaction to an address that we own. So this wraps up the overview and sort of line by line look at how you could make a transaction. Well, not just a transaction, but how you could make a contract similar to the MIST token. So back to you, James.
All right. Thank you, JT. How's my audio? Can you hear me?
Yep, loud and clear.
Perfect. So back to the slides here. So we just finished up the MIST coin. The other thing that I wanted to just discuss here and show some code is the this new contract that we've been working on called the SLP dollar. Everybody many of you are probably aware that the central bank digital currencies are in style these days, and so we've developed a script to allow CBDCs on Bitcoin Cash. And the primary requirement for CBDCs is that the token issuer wants to be able to freeze coins at will for anti-money laundering purposes. And they don't want to require the users to request some signature from their server for every transaction. In that case, if their server were to go down, then nobody could partake in commerce. So that's important that if the token issuer wants to freeze coins, they can just do that at will without requiring some signatures before every transaction. So here's a simple diagram. It just shows that there's some fiat token issuer authority, and they want to be able to freeze or unfreeze people's funds at any time. So you can see the user here has her funds frozen, while the gentleman below, he's able to spend at will. So I'll flip over to the code here. So I've forked the cash script repository, and in the examples folder where we have the SLP dollar contract, the front end of the contract shows what contract methods are available. There's a send method and a freeze method, and there's some constructor inputs that the token issuer would need to put in, like their token ID, their issuer's public key that's going to be used for freezing tokens, the public key hash of the owner of a new dollar, and the SLP amount that that is being held by an address, and then the state of whether or not this coin is frozen or not. So there's just these two functions. I'm not going to walk through all of the code here, but the most important one is when the user goes and tries to send the coin, there's this check that checks whether or not the state of the contract is frozen or not. And if it's not frozen, he can spend it. Otherwise, he can't spend it. The token issuer can use this freeze method below, and they can freeze and unfreeze at any time. And when they do that, when they freeze or unfreeze, the dollar holder's wallet will receive a notification that says whether or not his token was frozen or unfrozen. So his wallet will always know the state of his dollar token. And if you look closely at line 123 there, you can see where we're taking we're making sure that the hash outputs of the preimage matches the concatenation of all these different components, where you have the SLP message, the token output, the notifier to the token holder, and this notifier goes to his regular paid pub key hash wallet address. So since the address is changing, his wallet needs to know about this transaction. So that's how that happens. So that's kind of a cool application for SLP smart contracts. Another one that I've been working on, and I'll give a demo here shortly about, is called the SLP Vault. Now the scenario where this smart contract is valuable is when you want to airdrop or send rewards to anybody that has a Bitcoin address, and you don't know whether or not their wallet is compatible with SLP tokens. As we've discussed before, if their wallet is not compatible with SLP tokens, then their wallet will just simply burn the tokens. So you definitely don't want to be sending valuable tokens as a reward to just random Bitcoin Cash addresses, because the money will just get wasted. Instead, so the solution to this problem that we came up with was to create the smart contract vault that is derived from somebody's pay to pub key hash address. You can then airdrop or send rewards to everybody's SLP vault. And if they have a wallet that's compatible with this smart contract, the wallet can let them know that they've received some rewards. And for all of the regular Bitcoin addresses that didn't sweep their rewards, the token distributor can revoke those and take them back. So there will be no wasted tokens on wallets that are not SLP compatible. Yeah, we'll do a demo of that here shortly. Recently, in the last 3 weeks or so, I've been integrating cash script specifically into the Electron Cash SLP edition. And currently we do have testnet support for the SLP vault, and also another smart contract called SLP Mint Guard, which makes it impossible to burn SLP tokens. And the integration it's a manual integration. Smart contracts are added on a case-by-case basis because the UI requirements are a little bit too complicated to make it some kind of general purpose integration. But we've developed some tooling that makes it really easy to add a new smart contract. So you can see that in the GitHub repository. I'll just go ahead and flip over and do a demo real quick. So here's my testnet wallet for Electron Cash SLP edition. I'm just going to go ahead and create a new wallet from scratch. And we're going to have 2 wallets open. I'm just going to do a new wallet, new seed. We've got a new seeds phrase. We have the option to skip the seed backup, and the wallet will just provide us with a warning constantly until we back up. But this way we can get started quickly. And so to start off, we're going to pretend like the top wallet is somebody who just has a regular, they just have a Bitcoin address, and this is some address that we found on the blockchain, and we just want to send everybody some US dollar tokens, and we don't want anybody to burn their tokens. So what we would do, and this wallet on the bottom is going to be our token distributor wallet. This is where we're holding all of our tokens, and we'll create a new vault for the address that we found on the blockchain. And so basically what we do is just go to the address converter tab in Electron Cash, and then at the bottom on testnet, you'll see this SLP vault button, and you can generate an SLP vault address. Now, I'll explain a little bit later, but in order to generate an address, you have to first pin the smart contract details to your wallet. So this way, if you ever lose your your wallet file, but you have your seed phrase, you can always restore your wallet, and your wallet will still be aware of the smart contract. I don't know if you guys know this, but if you lose the details of a redeem script for a smart contract, that's pretty much the same thing as losing your private keys. So it's very important when you're dealing with smart contracts that you store the redeem script of smart contracts in a safe place. For Electron Cash, the way we've decided to handle this is to pin the details in a op return message in a little dust transaction to yourself, and that way you'll always have the details. So once we create this pinning transaction, our wallet is now aware of this new smart contract for this random Bitcoin address. So now that we have created that, we can go over here to the contacts page tab, and we can see all the different addresses that smart contract addresses that we are aware of. So this address is, let's just see here, his address ends with 8H4S. So I'm looking for an 8H4S, and this is all new code, so there could be a bug here. Let's see here. So he received a notification, so his wallet is aware of the contract. Oh, it says D's. Oh, I see. The address changed. Okay, so in Electron Cash, when you send something to an address, it never wants to send to the same address, so it updates the address. So what happened was it updated and it changed on me. So it's this first one here. It ends in DVZP, so I can see that. I can check here. Oh, I can copy the smart contract address, and I'll just keep things simple here. I'll just send him some Bitcoin Cash. So I've sent his smart contract Bitcoin Cash, and we can see in his wallet, since his wallet is aware of this type of contract, it says SLP Vault received new coins. You can go in here, and you can see highlighted in red is the cash script address. Okay, so now if he wants to sweep, he'll know that to get access to anything that's cash script, you have to go to the contacts tab, find the smart contract that has coins, right click. Now he can sweep the Bitcoin Cash into his wallet, or since I sent him these coins, I can revoke them. And so let's just for giggles, we'll pretend that he didn't touch these coins for a couple days. So what we're going to do is just revoke them. So in this transaction, we see the smart contract address. We know it's smart contract because it starts with a P. Pay to pub key hash starts with a Q. So we're going to revoke these coins back to our own wallet. Okay, so that's done, and he did receive a notification that his SLP vault was revoked because he didn't take action. And we have the coins here, and it shows in our balance the amount went up, so that's good. So that's the first smart contract that we added, and then we just added another one today, actually. And by the way, you guys are the first ones to see any of this stuff. It's all brand new. So there's the mint guard. So the mint guard's pretty cool because you can create a new token and put the minting baton in a smart contract that makes it impossible to accidentally burn the minting baton. And you can imagine that if you are, you have an important project like a US dollar token, you don't want there to be some possibility that you can destroy the minting baton, because then you can't print any more money. And we know how important that is. So now that the first thing you do is create a token with the minting baton. And once that happens, you go to the mint tool, check the box that says protect the baton. It said protect baton with mint guard contract. So now we're going to put this mint baton, we have to do another pinning transaction so that our wallet always knows about this smart contract. So now the wallet knows about the smart contract. So we're just going to mint 0 tokens because we're just simply transferring the mint baton, which currently exists in a pay-to-pub-key hash address. We're going to transfer it to the smart contract for guarding the mint baton. Okay, so now the mint baton is locked up into the smart contract, and you can see, if you see here, the blue is our receiving addresses, red is cache script address, and green is the SLP outputs. Okay, so now our baton's safe, but can we mint from this new baton? So we'll go back to the minting tool. Let's just try to mint 1 token. Now, some of this stuff's disabled because it knows that the baton is locked into a smart contract. So we can't change the address because it's stuck here unless we invoked the transfer function to a new owner. So we're going to mint 1. Okay, so we just minted 1 token. It shows up on our balance. And wrong one. Yeah, so there's the minting, and you can see the input was a smart contract because it's red, and the output baton goes back to smart contract, and we received 1 token. So it's like a miner validated mint baton now. Okay, so that's the 2 contracts that we have integrated so far with Electron Cash. And there's going to be more. I think we're going to do the SLP dollar will be next. So that'll be available on testnet so people can play with their US dollar token and act like they're the central bank. So the other thing that I wanted to show was the Meep tool, because once you get into building smart contracts, without Meep, it's basically impossible to understand what's even going on. So Meep just allows you to see the, I said earlier, it's a stack-based language. And so Meep actually simulates the stack. So what I'm going to do here, now here's the link. I don't know if this is pasted in the chat. I'm just going to switch over and paste it real quick. So if anybody wants to download that, they can go ahead, and then here's a big command. Once you have it installed, I'll give you the same command that I'm going to run. So hopefully it's not too big for this chat window. Oh, it's too big. I'll paste it in the Discord later. Okay, so just go through this. Make this nice and big so it looks good. Okay, so there's the Meep command. You basically just type in Meep, debug, -t, paste in the transaction, which is that thing. Oh, by the way, if you are in Electron Cash, to get a transaction, all you got to do is go down here and click copy. You copies to the clipboard. Once you do that, you can just paste it right into Meep and provide some of this other information. So obviously, the script evaluation is on an input by input basis. So you have to tell Meep which input you want to look at and evaluate its script. And since we're doing testnet, it doesn't know about any of these transactions. So you have to tell it the amount, just -a, it's a 546 input. I know that because it's a mint baton. -I, it's the first index of the transaction. And then the script pub key, which could be a little bit more difficult to get, but you should be able to get that if you're working with smart contracts. So now that we've run the command at the top, it says the script sig. So this is the part that gets encoded into the transaction input. The script pub key is the part that got encoded in the previous output that we're trying to spend. The redeem script is the locking script, which is, if you hashed the redeem script, it would hash to this value. And actually, you'll see that here as we step through. If you use F4, you can step through, and at the bottom, you'll see the stack, the actual stack, growing as we push more items from the script sig. Script sig is push only. You can't execute opcodes on there. So then we're in the script pub key now. That's where the cursor is, and now it's going to make sure that the redeem script hash is equal to what was in the script pub key. Those were good. And then we just start pushing stuff on. It's kind of a big contract, so we'll just hold F4. Now the red means that it's not executed because it's an if branch that we did not go into. Now we're into the other if branch, or the else, for our mint vault. I think that's what this is. Okay, so now we get to the end. At the very end, we have op check data sig verify op check sig. That's kind of where the magic happens. It can make sure that the transaction details that we're introspecting belong to this transaction. And then Bitcoin Cash has a clean stack rule. It means that you have to have you can't have an empty stack. You have to have only one item, and it has to be a non-zero value. So that's a successful script execution. In this, I love this tool. It's like the best. It's kind of fun too to run through. But that's how you'll actually be successful in smart contracts, is using combination of SPEDin or cash script and Meep. Those are sort of the three tools required. So I just wanted to hit on some important security considerations when you're building a wallet for smart contracts. Like I said earlier, if you lose the redeem script for your contract, because the redeem script is just hashed, and the hash goes on the blockchain. The script itself doesn't go on the blockchain. So if you lose the script, you'll never be able to verify that hash. And so losing a redeem script is equivalent to losing a private key. So this is why in the Electron Cash SLP edition, we took that pinning approach where, so what we do, we have a normal pay to pub key hash wallet. You start with a BIP39 seed phrase. And then when you're in the wallet, the user clicks to say they want to use some kind of smart contract. Before ever giving or generating the actual address for the user to use, we do a pinning transaction to make sure that the redeem script details do get on the blockchain. That way, if they get lost, you can always restore from seed phrase, and you'll get get your redeem script back. Now that can have a problem because you don't want to put for certain smart contracts, you may not want to put your redeem script on the blockchain. So, it's a case-by-case basis thing. So the wallet detects the pinning transaction in its incoming transactions. And then the wallet decodes the pinning transaction, verifies that it understands that type of smart contract, and then it allows the user to interact with that smart contract. So this is just a way to prevent the user from losing money. Okay, so that's all I had. JT is now going to walk through Introduction to Oracles with SLP.
Yeah, thanks so much.
Sure. Let's see. I'm just close this.
Okay. So I'm going to talk a little bit about how you can use oracles with SLP, but this is applicable to just Bitcoin Cash in general. But I want to show a sort of interesting, well, I think it's interesting way to use oracles. This is utilizing check data sig again, but this is checking for signed messages from, not just the transaction, but data from a third-party source. So you've probably heard about oracles in the past, but just for a quick breakdown, basically what it comes down to is somebody is signing some formatted data. They give you a signature, like you request it, and then you can use that data later in a contract. So this is useful for a whole wide range of things, but I'm going to go through one of the ways that this can be used. So one of the things with SLP is because it's not miner validated, some sort of contracts using it, there's no security if you don't have some source of, hey, this is a valid transaction. If you're trying to say, hey, let me look at this input, just within script, you're not going to know that because the miners aren't validating that data. That being said, you can do that using oracles, and you can actually have oracles that look at this sort of data and be able to say, hey, this is valid or this is invalid, just like I described. So this link here, this is a SLP validation oracle. It's an example of how you can use oracles for SLP validation. So for this, we like any oracle, you have some specific format that the server or whoever's signing is signing this sort of message. So for this, we concatenate TXID vout, which is just a transaction output index, token ID, token type, token value, is baton. And so you'll basically, for the implementation that I have in GS++, you'll give it a transaction ID and a vout. And if it's a valid SLP transaction, it'll respond with this data. This is a message, but also the signed value of this. For that, it uses Schnorr and it hashes this data. So you can look at sort of the spec for this too real quick. There's some differences if you're doing NFTs. But yeah, the basic idea is it'll just give you back the message and signature, and then you'll be able to use this later in a script. And the reason that this is done is you can say, hey, this server, this third-party server says this is a valid SLP transaction. But if you're thinking about this a little bit, you'll probably think, hey, you're just trusting that single server. That's not very smart. And you'd be completely correct. So one solution to this is using the same idea from multisig, where you have a M of n signature that you check. So you're checking, say, 2 out of 3 signatures and seeing if they're in agreement, or even if you can get 2 out of 3, right? Say a server's down or something. So there's and you can do it with higher amounts. And this sort of goes into the details for that. But yeah, the idea is every single server, all of the ones signing would have to be colluding. So this makes it a lot more secure than not only relying on a central service, but maybe it's a central service that's directly involved with your money. So a better step from that is relying on an oracle that knows nothing about your money. It's just telling you validation or whatever other information. But even better is if it's multiple different servers that have, no idea about who you're talking to, and they're reasonably separate. So using this idea, I created a script for offline buy orders. Buy orders are saying, hey, I want to buy, some amount of tokens, putting up this much Bitcoin Cash. So we have this script here that you might want to look at and reference during this. So yeah, this just goes more into how it works. Transactions useful to look at for this specific contract. So for this, we have two different inputs. One is 4,000 Satoshis right here. And then we also have 100 M10 tokens. The outputs from this are 100 M10 tokens and 1,000 Satoshis. So look at these. Oops. I'm having trouble selecting it, but this one right here, this address and this address, you can see that they're switched. So this person's spending 1,000 Satoshis on these tokens. Well, they're the thing with it is there's a transaction fee, so that's why it doesn't match up exactly. But and the reason that the other transaction is different is because it's actually going to the original pub key, not the special contract address. But yeah, it's doing a swap between BCH and SLP at a specific amount. So again, I'm going to go through sort of line by line on how you could make something like this yourself. For this contract, I had to use some sort of macro system to do the M of N idea for multisig, because there's not a op check data multisig. So this just does it in script. So I don't know if you're familiar with handlebars, but it's just a simple templating language. You can use it in JavaScript or a few other languages, but that's not too important. But what it's doing here is just basically creating multiple different validator public keys with different names for this. So, and yeah, this is in Cash script, so it's super similar to the Mist contract in Spedin, but it has a few different differences, and there's a pretty cool difference with regard to covenants. So yeah, likewise, instead of challenges, these are called functions. And we're going through each of the ends and creating, similarly, another incrementing index with that. So yeah, you're passing in how much BCH you'll receive from this. So remember before how I showed 4,000 and that turned into 1,000? Like, why was it 1,000? Well, for that transaction, there's 3,000 Satoshis used as fees. So you can select less to come from you, and that amount will just go to the miners. And then we're also including some pre-images for the previous outputs. And yeah, when we're actually calling this way to spend this, we have to pass in the signatures that we grabbed from the validation servers. So when you're actually prior to when you perform a transaction, you actually have to hit those servers, the ones that are specified. And there's different ways for signaling, but to be able to handle those different public keys for this specific contract, you need to, get valid signatures that map to those same public keys. So for this, it's pretty simple. We're just checking the signature for the spender. That's correct. If you don't do this, maybe anyone could spend it, as long as they followed some of the other rules. So, we're also checking the hash previous outputs. So this is one of the big differences between cache script and SPEDN, and a really cool feature. So you notice maybe in the last slide that there is no check data sig on the preimage. So if you're using cache script, it actually automatically will generate the code for extracting out the specific data from SIGHASH, the SIGHASH digest, like described here. And not only that, it'll also check the check data sig. So it'll ensure for you that, as long as you're using covenants, it'll handle that, because it's just a super common pattern. And it's only really relevant to the specific use case. So if you're using like tx/ or tx dot hash previous outputs, it'll generate all the code that you need, and you won't have to worry about doing the crazy parsing like I showed for the MIST contract. So for this, we're going to require that the second input be SLP. So we're taking when the user's spending this transaction, they're putting in the preimage, and that's going to be 72 bytes, and we're grabbing the second of those two when it's split halfway by 36. And why it's 36 is it's TXID plus VOUT, so 32 and 4. So this is the left side, and this is the right side, was splitting 36 by 32. And then we're going to build up the preimage right here for validation. And this is actually matching the same format that the validation server is using. And this would be the only way that this would work. So it has to match. You have to match with whatever sort of validation or Oracle server that you're using. It doesn't have to be a validation server, but normally any of them will have some sort of listed spec for how the items are concatenated and what that looks like. So this is just matching what the server is actually signing. And now we're going to do the fake multisig. So this is doing check data sig between the validators and the preimage that we just created in the last step, along with the validator public key that the creator of this buy order had input. And again, this is just using macros to go through each of the different public keys, and we're adding up if these match. So it'll just not add anything if it doesn't match. And then our require, this is the same as verify and SPEDN. We're verifying or requiring that we have at least M valid signatures. And this M value was created at the start of the instantiation of the contract. So it's a 4 of 5 or 2 of 3 or whatever it is. And this part, this looks a little funny, but it's actually just compressed down. Instead of having individual names for each of these things, I just took the bytes for what would be required for a valid SLP transaction. We're using token ID.reverse because, for endianness reasons, the validation server uses different endianness than SLP on the blockchain, and the same for token value. But otherwise, this is just adding, this is just building up a output. So the reason there's 8 right here is that's pushing 8 bytes, and then there's token value, which has to be 8 bytes, and likewise 20. which is really 32 for the token ID and so on. Then we're creating two other outputs. This is a built-in function for cache script that just generates something that looks similar to this as far as hexadecimal, but it's just creating pay to pub key hash outputs. So the first pay to pub key hash output is to the creator, and then we're doing another one to the person who's actually running this transaction when they're completing it. So they're getting whatever amount of BCH that they wanted, up to the amount that the creator made available, because otherwise, miners wouldn't allow a transaction that gave more BCH to someone than what existed. And then we're doing hash 160 on the public key. So if we passed all of these different steps, the transaction is valid and a swap would have occurred. So there's another part to this contract that's called cancel. And say someone puts up a buy order for some tokens, but later they want to cancel it. They just want to return their BCH and be able to use it. They want to use it in a different transaction. That's absolutely fine. We shouldn't just require people to have their Bitcoin Cash sitting there forever unless they acquire those tokens to finish the transaction, right? So they shouldn't have to perform a buy order on themselves. They should just be able to cancel the order and return their Bitcoin Cash. So this is actually really, really simple. The creator can just provide their signature and their public key. This is checked against the instantiation of the contract. And all we're doing is checking that the signature is correct and the creator can return their coins back to themselves. So this is just one way that you can use oracles with SLP. And this is like I picked this because it's kind of an interesting use case where you can use oracles for things other than maybe just price or something like that, like binary. This is sort of like a binary oracle, right? It's either valid or not, but you can actually use them for a lot of things. The main thing that everyone's focused on is pricing of assets, but I think there's a lot of really cool things they can do outside of that. You can do that, prediction markets, staking systems, pretty much anything where you can have different servers providing some sort of data and being like, hey, is this valid, or am I going to sign for this? Am I going to allow someone to make some transaction based on this information? And so you can actually use that for like a really large amount of things. And I think utilizing the federated approach, like how this validation oracle uses it, makes that a lot safer compared to how most oracles work today. You're not relying on a central source of information. And you'd really require collusion across such a large scope that it's just way safer in general. So thank you. That's my presentation on validation oracles.
All right. Nice. I think we only have a couple slides left. So we just wanted to touch on some of the common problems and workarounds that you're probably going to see. The most common is the signature pre-image is larger than 520 bytes. 520 bytes is the largest size of the largest string size that can be on top of the stack. So you have to stay at or under 520 bytes. To fix this issue, and the reason why you hit 520 is because you have the redeem script is included inside the preimage, which in some cases is totally useless. It's just like wasted. You're paying too much for the transaction. You don't even need to use that. So you can use opcode separator to get under the 520 bytes. This is pretty easy. We did this with the SLP mint guard. I can just show that real quick. And to do that, basically, you just instantiate the contract with the hash of the base script, of the uninstantiated script. And then each function will just check to make sure that the base script, and you do have to pass in the base script with the in your script sig. But as long as that's less than 520, you'll be fine. So the mint guard is a good example of how to get around that issue if you face it. The other thing that I've seen a million times is signature verified fail. This is because of a problem with your signing code. You might feel strongly that there's a bug in Bitcoin Cash. I've felt that way before, but pretty much it's probably a problem with your code. So a lot of times what's happening is you're probably signing the wrong pre-image hash. And this can happen because there's different sig hash type pre-image requirements. So sig hash type is another one of these things where you're going to want to do a little bit of reading about. Basically, there's different types of, you can sign different parts of the transaction. So you can say that I'm going to sign this input and I want to make sure that I sign all parts of the transaction. That's typically what you do. When you sign something, you sign the whole transaction. But you might want to allow anybody else to pay, and you don't even know who they are. You're just going to throw up your partially signed transaction somewhere, and somebody else is going to come along and pay it. So you can't possibly sign that part of it. So that's where sig hash types come in. There's a specific sig hash type that allows anyone to pay. And those different sig hash types have different pre-image requirements. So the other part of the other problem that happens is you'll put together your pre-image and you put in the redeem script in the script code part, but you don't remove all the opcode separators. And so that's like with the mint guard that I showed, there's opcode separators. Actually, I don't think I've touched on those, but you use those to reduce the script size. Those get removed in the pre-image script code. And then also the opcode separator has specific rules. So if you do use those, then you only provide specific sections of the script code in the pre-image. The other issue is the script exceeds 101 operations. This is pretty common, not much of a workaround. Just try to make your contract more simple. JT has some ideas for using some like chaining and looping, but I don't think anybody's ever done that before. It's pretty complicated stuff. Same thing with if you have a redeem script that's larger than 520 bytes, then there's not much of a workaround available for that either.
There's a quick question here, James, about byte size limit. Can Schnorr or Mast help keep scripts under the P2SH byte size limit?
Yeah, so Schnorr has a smaller signature. So possibly, usually the signature doesn't actually come into effect, because you're not going to put the signature in the redeem script. Mast is part of Bitcoin Core, so probably more likely that in Mast that would help resolve some of these issues, because I know in Mast you're only revealing parts of the script, like in a tree, a signature, or a tree hash or something like that. So yeah, Mast probably, Schnorr probably not. I could be wrong though. And I think that's all we had. If there's any other questions, feel free to ask them.
There was a question here. I think JT kind of addressed it in the comment below, but the question says Oracle. I think they're asking if Oracles get a fee for validation. I'm not 100%. It would be pretty simple. JT, you seem to grasp what they were asking. Do you want to jump in and address that? Just
yeah,
we have it?
yeah. I mean, I had this thought when I was building it, but it just added more complexity that wasn't really needed for a proof of concept. So yeah, I mean, one of the things that's pretty useful is paying people for their work, or even if that person's a computer. And yeah, it's a great idea. I mean, if there's some service that's validating transactions or validating outputs and they're providing a good service, that's the only way that they're going to be able to keep on running. So yeah, I mean, you can have smart contracts using covenants require payments to those services. I mean, those could be built right into it, and if you're utilizing those, you have to do some sort of output to them. When you're looking at some sort of spec that takes into account different, just let me put in any public key and any signature that'll fit with that. That's kind of hard to actually fit in with a dynamic fee structure or something where people might want to change fees over time or whatever that might be. So it's not a super simple way to solve that problem, but like it's definitely possible. Yeah,
cool.
So I think that sort of covers it.
Nice. I had a question for you guys about the CBDC smart contract and how that kind of fits into the vision of, like decentralized, free, kind of peer-to-peer interaction, where in these CBDC proposals, they are like saying like we can freeze your account at any point in time based on our jurisdiction, based on our sets of rules and stuff. So how does that kind of fit into the ethos of peer-to-peer? Sorry, you're muted, James.
Yeah, I would expect a lot of pushback on these sorts of ideas, but ultimately, I mean, we're early days in Bitcoin still, or Bitcoin Cash, and people are free to use Bitcoin Cash if they don't want to have their funds being frozen or but if a government wants to use blockchains to issue their currency, I think we should be happy to help them. I mean, I feel like we're in a situation globally where we need to evolve our technologies, and blockchain is a very powerful tool to help everybody evolve. So I think we should be happy to help the legacy systems upgrade and do their thing. I don't think it conflicts with the ethos. It's just like another use case. And you're not, governments aren't going to get rid of their currency. They're always going to be around. So we just have to, work with them instead of trying to fight them. And people can figure out on their own what kind of currency they want to use.
Yeah, I want to add to that too. Like, I mean, what do people really want to use, right? If they have the option of one money where some person, 1,000 miles away can just freeze their entire assets and unperson them, well, that's fine. Like, they're more than free to use that sort of technology and go about their life. But if they want to use something that, that's impossible to do, they should also be able to do that as well. And so I think it's sort of like a self-solving problem. Like, if you gave those two options to someone, why would anyone choose the first option? It doesn't make any sense. So I think either way, it's almost a certainty that governments are going to utilize blockchain and use it to mass censor and control populations on a global scale. But I think at the same time, unless people really are building this stuff out and making it possible for people to have a better option, people will just choose the better option. And if people choose not to, that's their own choice. And I don't know, they must be kind of crazy, because that doesn't make any sense to me. But they're free to do that, I guess.
I think with the I think with the price volatility that we see with Bitcoin, it makes a lot of sense for fiat currencies to still have a role, and you're still going to have to pay your taxes and fiat currencies, and you might to take loans out. There might be more options there. So I think that it's not black and white; it's a spectrum, as always.
Yeah, for sure. I definitely agree with like essentially what you're describing is Gresham's law, right? Like, good money will weed out bad, quote unquote, bad money. Yeah, I guess the question was like, why spend energy in actively building bad money? Yeah, and that I guess comes down to a personal choice.
Well, I think maybe it's sort of like there's a transitional phase possibly where we all still primarily use government issued money, but it's on a blockchain instead of in regular databases. And we can do that to sort of avoid a total collapse of society. It's like some kind of transition possibly.
Very interesting. There was a comment in the chat about your paste bin that you had. Some folks were having difficulty accessing it. So if you could maybe repaste that.
Okay. Yep, I will. I tried to paste it in the Discord, but it was too large. I'll put it in a file and upload the file. Hopefully that works.
Cool. While you're doing that, let's take a quick peek at our poll here. Let's see. So most folks didn't know what P2SH was, but now, after your amazing in-depth presentation, I'm sure they have some sort of idea and they can begin implementing it into their project. So that's awesome. Likewise, a lot of folks haven't used Cash Script, but there were some folks in here that have used Cash Script before, and so hopefully we've given them some good information along the lines of getting them involved. And yeah, a good majority of folks have written smart contracts, interacted with smart contracts in one way, shape, or form. So that's very cool to see. Is there any more questions from the audience? We'll wait a couple of more seconds here as you get the paste bin all sorted out.
Yeah, it looks like I cannot upload files in this chat, so I'll just upload it to the Discord.
Okay, cool. And that brings up a great point. Actually, I'm going to come back on screen here as we wrap up, and I will take that off. Very cool. So yeah, that brings up a good point. If you haven't already signed up for Blockhack, time is running out, but there's still a little bit of time. You're not going to want to miss out on this opportunity to build your MVP, build a business in this space for this hackathon, and submit that project, submit that business idea for seed funding so that you can continue to build out this idea in a ever-growing digital blockchainized world. We want to see strong business models being built and continued through this hackathon and beyond. So take a look just below the screen here. For those that are on desktop, there'll be a link for the Blockhack Global Resource Hub. That is where you'll find all our links to our webpage where you could sign up, as well as links to our Discord, where you'll be able to find the link that James is posting right now. And you'll be able to find everybody that's hacking alongside you. And if you need any help with your project, if you need some mentorship, we have entrepreneurs willing to mentor you and go one-on-one and help you build out your business idea. So go ahead and check out our resource hub, and we have some more workshops and talks coming up for you. So if you, I think I'm pointing the right way, if you click on the follow button, you'll be able to get notifications for our talks as they come out and as we put them up on our page. So go ahead and give us a follow, and I think we are wrapping up. Is there any final words from you folks, James and JT?
Just want to wish everybody good luck and keep up the hard work.
Awesome.
Yeah, I wanted to say, if you're concerned about government involvement with money, it's really important to build out solutions that can outcompete those whatever they bring to the table, because I'm sure it's just going to be terribly implemented and everything else. So, you can probably start out as someone who doesn't know anything and come up with something a little bit better right off the bat. So it's really important that as many different ideas come and are actually being worked on, and I think that's really the only way to deal with mass censorship of money.
100% agree with that. That's a great note to end off on, folks. The ball is in your court to build a better solution, build a better future. So I would like to see you all in the Discord, and I will see you in 2 more days when we have some more workshops and talks for you. And until then, I'll see you in the next workshop. Take care, everybody.
See you, everybody.
Bye.